Chemical Equilibrium Part 10, Le Chatelier's Principle and Temperature Changes. Okay, so this is the last part of our discussion about Le Chatelier's Principle and stressing a chemical system. Chemical reactions that are already at equilibrium like to stay at equilibrium. So any factor that disrupts this is considered a stress. Now in the previous two videos on Le Chatelier's Principle, we talked about adding and removing product or reactant, and then also about pressure volume changes. And the last stress that we need to discuss is changing the temperature. And so we're going to be thinking about this from the same mental framework where if a chemical reaction at equilibrium is stressed, the equilibrium is going to shift in the direction that counteracts the stress applied. So how does this apply to temperature changes? So temperature changes are a stress on the system. And the way that this works is that when we change the reaction temperature, the equilibrium constant K no longer has the same value. So remember, the equilibrium constant is the ratio of the forward reaction rate constant divided by the reverse reaction rate constant. And when we change the temperature, thinking back to the Arrhenius equation, that equilibrium constant no longer has the same value. But the value for Q that we calculate for that system remains the same. So the equilibrium is going to shift so that Q is equal to K at the new temperature. So how can we figure that out qualitatively? So the easiest way to think about this is to think about delta H, which is enthalpy change, and think about heat as a reactant or product in the reaction. So for instance, an endothermic reaction absorbs heat from the surroundings. That's a positive delta H in the forward direction. So heat is a reactant. So you have reactant plus heat going to product, and that's an endothermic reaction. An exothermic reaction is the opposite. So remember, these are the reactions that feel hot. So they release heat into the surroundings in the forward direction. So that means heat is a product. So we're going to have reactants going to products plus heat. So how can we use this concept to figure out which way the reaction is going to shift when we change the temperature? So here's an example. We have nitrogen dioxide in equilibrium with dinitrogen tetroxide. So the delta H for this reaction is negative 57 kilojoules per mole. So that means that it is exothermic. Now, if we increase the temperature, which way will the equilibrium shift? So we're going to keep in mind that delta H is negative, so that means heat is a product. So let's go ahead and put it in the reaction. When we increase the temperature, we're adding product. So if we add product, then the reaction is going to shift toward reactants. So for an exothermic reaction, if we increase the temperature, the reaction is going to shift in the reverse direction because we're adding product, which is heat, and so we're going to shift toward reactants. Now let's mix it up a little bit. Let's both reverse the reaction, so write it in the reverse direction, which is what I did here. So dinitrogen tetroxide now is in equilibrium with nitrogen dioxide as a product. And when I did that, I needed to change the sign on the enthalpy. So remember, when you reverse a reaction, then you give delta H the opposite sign. And now we're going to decrease the temperature. So we both reverse the reaction and decrease the temperature. Pause the presentation and figure out which way this equilibrium is going to shift. Okay, so let's go ahead and set it up the same way. So now delta H is positive, so that means heat is a reactant. So if we write out our reaction the same way that we did before, and we decrease the temperature, so we're going to decrease temperature, that means we're removing reactant, and so the reaction is going to shift toward reactants. We removed reactant, so the system is going to try to replace it by shifting toward reactants. All right, so here's another little mini quiz. So the temperature is increased on this reaction. Which direction is the equilibrium going to shift? Okay, so again, heat is a reactant because we have a positive delta H. So we're going to write heat in here as a reactant, and we're going to increase the temperature. So we're going to add heat. So we're adding reactant. So the reaction is going to shift in the forward direction toward products.